Hello, everybody, and welcome to kind of this Thursday edition of Water Talks. A little different than, obviously, not that different, just Tuesday to Thursday difference from a normal week, but it's not an April Fool's. We're actually, just doing standard Water Talks here with you all. Just a couple minutes here, let more of the attendees kind of filter in. We had great kind of registration for this, and it's great to have Patrick here with us to kind of go through some hydraulic modeling kind of issues you might run into and how to quickly kind of address those here. So with that, let's just kind of get into the topics today and kind of what we'll be looking at. So, and your host today, myself, Tim Medeiros, solutions engineer here at InfoWater. I've been with InfoWater for 4.5, coming on 5 years now. Can't believe it. Working as part of the support and kind of pre-sales for InfoWater. Happy to be hosting and letting Patrick Moore do a lot of the talking here. Patrick, do you want to go ahead and introduce yourself?
Yes, I've been also here. I think we were both hired within a month or two of each other. But I worked as a consultant for about 15.5 years, and then I've been here a little over 5 years, mostly in, well, I guess all in technical support. But really glad to share a lot of common things that people run into that may hopefully help people.
Yeah, it's great to have you on, Patrick. Whenever we have you on, we get tons of engagement, lots of questions, and you've been a helpful resource and person for me just to InfoWater and all my hydraulic modeling questions. So,
Awesome.
Great to have you with us here. And so, for those of you, maybe this is your first Water Talk, or you've joined quite a few of these since we started here in April. The goal for these really is to engage and get your questions. Patrick's got a lot of information to present on, and in fact, you've got a handout for those of you who can see this in GoToWebinar. There is kind of a PDF handout of the slides that Patrick's provided ahead of time. So if you want to kind of follow along with what Patrick is showing, kind of in the different errors and solutions to those errors we might find within a hydraulic model, feel free to download that, and we'll hopefully send it. We'll have that available to folks afterwards if you want to, if you didn't get a chance to download. But again, please be asking your questions, yeah, looking forward to getting into it. And for those of you that do follow Water Talks on kind of a weekly basis, we will be back to Tuesday next week. So this is just special Thursday edition. We will be back to Tuesday next week, and we do have a great presentation on the sewer side with Freeze and Nichols. We'll be presenting kind of ICM within wastewater treatment plants. That's pretty exciting. So be sure to join that as well if you're interested. But with that, I think that's all I've got here. Everyone knows kind of the ground rules. Hopefully everyone can enter those questions in to the GoToWebinar chat there, and I'll turn it over to Patrick here. I'll let you share your screen.
Our little handover here. Let's see.
There you go, sharing.
Come on now.
There you go. You should have got it now.
Sorry, I've had to move my computer over here, so my mouse is backwards here. Okay, so you can see the slides here. Okay. Let me get to here. Okay, awesome. So let's start out with talking about some common model run issues that people run into and how to solve them. Generally, you can break these down into 3 primary categories. First is, hey, I'm unable to create the input file. So I go to run and it gives me some errors saying, hey, I don't like something. And so it's not working. That is a very common thing that, can happen. Generally, that means there's something in the setup that caused the model to be unable to create that EPNet input file used by InfoWater or InfoWater Pro, mostly due to either bad or missing data. Second common thing, and then we'll talk about all these in a lot more detail in a little bit here, but just some grouping, some overview, is, hey, I went to run my model and it didn't solve, it didn't give me any output. It gives me some errors, and most of the time that is either due to, again, either an input error or it's having a convergence problem. It just can't converge to a solution. It's a numerical analysis of what it uses to solve all the data that you put in, and sometimes based on what it is there, it's just unable to do that. And so what to do when that happens. The third big group is, hey, my model did run some, like if you're running an extended period run for 24 hours, it's pretty common, and it stops at maybe hour 12 or hour 10. It didn't get the entire length. What happened and how do I fix that? That's another pretty common grouping of things that happen. So in general, when those things happen, I mean, it's really helpful if you have at least a basic sense of some of the common typical errors that can happen and then how to resolve them. That's kind of part of what we're going to talk about today, of look at each of those three groupings and kind of some typical things that happen and generally what you need to do to resolve them. The second thing, and I think this is really important, is just to be systematic. Solving almost anything in models, you really have to be, keep good notes. This is what I did. This is what I found. Know where to look for where the problem is. We're going to talk a lot about the full hydraulic status report and how that's kind of the key to solving a lot of these. That's really usually going to tell you the problem was here. Then next, once you know, oh, okay, these are the elements that had the problem, now how to review those elements and say, oh, okay, there's the problem. Then thirdly, fixing it, resolving the problem. And then lastly, going on to your next issue, and not getting intimidated. Sometimes it can feel like, oh, there's so much things there, I can't figure this out. Just be systematic, work through them one at a time. Generally, you're going to find it'll all work itself out. Thirdly, definitely learn from each error that occurs. If you keep good notes and reminders, I'm a big fan of, hey, when something happened, thinking through what can we learn from this? Is there something we can do in our process next time to help us avoid some of these common mistakes? That's, just being wise. I found that really helps to minimize the impact of these, but or at least know, okay, when this happens, do this, do this, do this. Generally, that's half the battle. Fourthly, I think, especially when we're getting into the run issues, the more over the years that I think I understand better understood what the EPNet engine is doing, I find that's really helpful. There's a whole section at the end of the EPNet help file that kind of talks about here's how I solve and how I go through it. It's obviously, complex reading, but, if you ever really want to understand why certain things in EPNet, based model, uh, might not like certain things, it's pretty clear generally when you start looking at that. And so, over time, the more you kind of get a better understanding of that, it really, really helps, because then it's like, oh yeah, no wonder it didn't like this. Oh, no wonder it didn't like that. So let's start out with that first group of errors. Hey, what if my model is unable to create the input file? It's giving me errors. What is that going to look like? Generally, you're going to see a gray light in your run manager or a no light if you're an InfoWater on the run. That pretty much indicates the software cannot create that EPNet input file. There was something that it has checks that built in, hey, look for these things. If this is there, don't even try to create the input file because there's a problem. Most of the time, that's going to come up with either one of two pop-up messages. The first one I don't know why I call this, but it's like group of 10 errors, because it usually says you have 10 or more errors of this. And it'll list some IDs that are there. Those are the most common. You just kind of got to work through those 10 at a time. And, once you've finished those, then it's like, okay, I'm now ready to look at the others. Other times you may get the full hydraulic status text box that pops up and says, hey, you had this kind of error and I just couldn't handle that. So those two are pretty common. The last place, if you don't see either of those, is look at the message board in the software, because there's certain messages that only show up there. So if you press it and you're like, there's nothing happening, what's wrong with this? Look at your message board. That's that other place that's important. So let's look at a couple of key common input errors that cause this. So the most common, I would say, is something that's called an illegal value on data. That usually means, hey, there's some kind of field that you didn't populate, and I need that to solve. For example, on pipes, the roughness, length, and diameter all have to be non-zero. So if you added a pipe but forgot to populate the roughness field, not going to run. Or if it had some diameter that was unknown, so it was 0, not going to run either. So it'll tell you, though, it'll list IDs. Hey, these things had illegal values. I can't run like that. And so you just got to review those and be on there. Things like if my take initial status was higher than my maximum level or lower than my minimum level, since that's physically impossible, it will say, hey, I can't solve it if that's the case. Another common one, this one happens to me a lot when I had a tank or a reservoir for something really quick, and I'll forget to populate the type field. In a reservoir, that's the fixed head or the pattern changing head, so that kind of type field, make sure those are on there. Those are generally the most critical fields that if those are not there, model can't solve. So check those. The next would be, hey, you're referring to some element that is not defined in the input file. Most common reason for that would be a pipe that has the pipe is active, but one of the two nodes connected to it are not active. And so it's like, when it's on active, it's like it doesn't exist. And that will say, hey, I don't know how to run without those things there. That's usually involved in what's called the facility tab of your scenario manager, where it says these are the elements that are active for this scenario. You usually got to either check the fields for that element because I had a query set and I forgot to populate something, or I just messed up my facility definition. But find that's pretty common. Another common thing is if I referred to either a pattern or a curve that I forgot to create. Not often this happens, but it definitely comes up. It will tell you, hey, I don't know how to solve that because you're asking me to do something that doesn't exist. So you got to it'll tell you the idea of that, either create it or change it to something that does exist if it was one that you got rid of. Another thing is an invalid pump curve. This comes up fairly commonly. What happens, and this is one of those quirks of EPANet, when Lou Rossman wrote it, he assumed all the head values would be decreasing as the flow values were increasing. And so there's some, I think they're usually vertical turbines, that you might have a slight rise before it continues down. So you just have to cut off that rise so that all the values are going down. Generally, your pump's not operating near that point where that rise is, so it's not a big deal, but just, hey, that's something that EPANet cares about, because it does InfoWater and InfoWater Pro does, because that's our primary engine. Another thing is any model has to have a tank or a reservoir, at least one, because those are known head values. It can't solve the equations if it doesn't have a known head to start with. So if it's missing, then it'll tell you. Another common one would be, hey, I have a pipe that has a check valve yes field on it, and so those pipes cannot have a closed initial status or a control that would open or close the pipe based on system conditions because of the check valve. So anytime it senses that, it's like, hey, I can't run like that, fix that and then I'll run. So watch out for that. Obviously, if I've got an orphan node or a group of orphan nodes, something that's not connected to the rest of the system, it can't solve the head equations, it can't supply demand, not going to solve. Find the IDs of what it says, figure out how to connect it. Could also be a facility issue that I forgot that these shouldn't be active and they are, fix that, or I just forgot to connect it. Another kind of common thing, because in the EPANet engine, pumps and valves are lines, but in InfoWater Pro, they're points. We do that by kind of putting two nodes that you don't see and drawing a line when we do the EPANet engine. But in order to know the direction of the line element when we send it to EPAnet. We do that from the both pipes that are connected to the pumper valve. So both of those have to be in the direction of flow. If they're either both going away from the pumper valve or both to the pumper valve, it'll give you an error, and that's one that's almost always in the message board, so watch out for that. But you just got to fix those so that they're both in the direction that the pumper valve is supposed to flow normally to fix it. Obviously, the more models you build, the easier this gets, because you see, oh yeah, I remember this. Oh yeah, I did this last time. Okay, and you just get used to it, and then you start checking for those before you're running. But again, be systematic. Don't get discouraged. You just work through those groups of errors, and obviously contact support if needed. So input errors, that's what's there. What about, hey, I go to run my model and I'm not getting any solution at all. Basically, what that means is I hit the run button, I'm getting a red light. It says, hey, I tried, but I could not get an answer. So there's no output to review. Those are always more challenging. Tim, was there something or?
Yeah, I guess one question before you kind of move on to this different set of errors here. On that last section, Mickey had a question. Is there a way to list all the 200, those 200 codes, 200 code types?
They're in the help file. There's usually like a troubleshooting section, and it'll say like warning and error messages, and it'll list those. It'll definitely read what they are, in the error, but that's usually the place when I want to find that list. I'll go there to find it. But that's most of the common ones I did put in here, but that's the best place to find it is in the help file.
Perfect. Thanks.
Awesome. So again, back to the solve problems. Usually when this happens, you'll see that status report pop up, and that will tell you, hey, here's what was wrong. And so if that's an input data issue, like I think a disconnected node or something that's on there, there's certain things that'll show up in that run text report, that hydraulic status report. Those are usually input data issues. If it's that, just like what we talked about before, walk through those and fix those. Let's say there's some place in the system that has demand, but there's a disconnection somewhere and it can't get water to it. That's essentially what a disconnected node error often means, at least in terms of EPAnet. I must satisfy demand, and if it can't get water to it, it can't solve. Thirdly, if it's reaching its maximum trials, and you told it to stop. We'll talk about that a little bit more in a few minutes when we actually see those slides. But that often means it's a convergence issue. There's something keeping it from converging to a solution. And so you really want to look at your some adjusted simulation options. We'll have some recommendations here in a minute of things that we think are the best for helping convergence. Doesn't guarantee, but if it doesn't solve with those, there's usually something in the setup. And then actually how to use that full hydraulic status report to troubleshoot the problems if it's a convergence issue. So again, input data issues, we talked about that. If it's not the demand, that full hydraulic status report is definitely going to list, hey, these elements, I could not satisfy their demand. Figure out what's going on with those. Another thing, if your initial tank level is set to the minimum tank level or the maximum tank level, that's going to cause all the pipes connected to that tank to temporarily close. That may be the only source of supply for a certain pump station and beyond it. Obviously, that's going to cause a model, hey, I can't get water to it, so I got to review those. I got to resolve them. Again, the model convergence issues. We'll talk about these in a couple slides. Let's look at those recommended simulation options. The ones that we found often are very helpful in helping people with models that aren't converging. I'd say in the last 5 years, these default settings, somewhere between 60 and 70%, if somebody says, hey, I've got a model that's not converging, I'll put these in, and at least 60 or 7% of the time, that's enough and it solves. That's why, these kind of are our default ones. What are some of the causes when a model is not converging? Well, usually, as we point out up here, it's elements fighting for control of the HDL. That's most often two or more PRVs that are both trying to maintain a hydraulic grade line. That's something in the ePainted solver that it really wants to keep that hydraulic grade line associated with that pressure setting right there. And so if two are too close to one another, it's like, hey, I want it to be here. No, I want it to be here. They just cannot converge with both of those being there. Same thing can happen in the real world, and that's where you get valve chatter. You'll see it more often in the model because the model's a little more sensitive to it. Another common cause is if I have check valves that are switching, or if I have unstable simple controls, like this is where pressure-based controls in the model can be very sensitive to this kind of problem. Something where if turn on at this low pressure, and so the pressure's too low, it says, hey, I should turn on, but as soon as the pump turns on, then I've got another pressure setting to turn off, and then it's like, oh wait, now I'm too high, and so it just goes, I should turn on, I should turn on, I should turn on, I should turn on. It doesn't know how to handle that. So it's an unstable, that's what we mean by that. We'll talk about that in a little bit more as well. The convergence settings that we're talking about that help are found in what's called the simulation options. Those are both on the general tab and the advanced tab, and I'll show slides of those in a minute. These settings, like I said, often can solve many issues directly, and if it can't solve with these recommended settings, that's pretty much a pretty clear indicator there's something in the model setup, something in what it's doing that's making it not possible, whether it's an unstable control or PRVs that are fighting. I just need to do some separation to solve that. So where can you find the simulation options? So the first place is if I go to the Operations tab in my Model Explorer, I'm going to see a list like right here in the middle of different options. One of them is your simulation options. So I can either expand it and double click on the one that I want to edit, or I can highlight it, right click and choose edit. That's going to open up the simulation options box. Or I probably do this more often myself, just I open the Run Manager, go to the Standard tab in the middle box, those little three dots right here on the slide. That will take you also to the same slide. One note, the InfoWater Pro has a couple, it kind of rearranged the order of where these are. That's a little bit different from InfoWater, and there's a couple of options that are different. The nice thing in InfoWater Pro is they put all the convergence criteria on the same side. In InfoWater, you've got some that's on both sides, so it's kind of nicer in terms of organizing, but like this max unit head loss error, max flow change, those are newer things that you could read about in the help if you're interested in that. So some of the key things in these settings, and on this slide here we show them, maximum of 200 trials. There's a lot of times we'll see people who have a model that's struggling to converge and they'll use 1,000 trials. Pretty much if a model is not converged in 200 trials, it's not going to converge in the next 800. So 200 is a pretty good place to start. Most models should definitely converge most of the time in under 50 trials. So if it's not solving in 200, there's usually a reason. So second big thing that we would recommend is a relative flow error. In InfoWater, that would be called the accuracy. It's the same way EPNet calls it, the accuracy. And there's a range of acceptable numbers there, 0.01 to 0.001, with 001 generally being the sweet spot of where we would recommend to start. Another key value is the after max trials, or what's called unbalanced in EPNet and InfoWater. There's two options there. One is to stop, and this is what's key to understand. If it reaches these maximum trials that you say, and you have it set to stop, then it says, I can't do anything else, I'm done. and so that's going to stop the simulation right there. Because it's harder to troubleshoot a model without any output, I'm more of a fan of the continue, which will allow some additional trials with restrictions. But I would keep those between 10 and 50 that are on there, the extended run trials. 10, I think, is EPANet's default. 50, if it's not solved by then, it's not going to solve. So I wouldn't go any more than that. 50 is definitely more than adequate if you do that. The max unit head loss and max flow change buttons, those are something that are only in InfoWater Pro. As I said, those will be additional checks that you can say, hey, if it meets this, go ahead and stop. I'm comfortable with that stopping at that point. Essentially, what the solver is trying to do when it's converging is getting that relative flow error below your accuracy, number. So when it's solving, it gets a relative flow error that it's solving each iteration. And once that is below your accuracy and all its secondary checks that it does on controls, because there's certain things that'll do it, are satisfied, then it'll stop. And so that's usually what it's trying to do. You'll see those numbers decreasing if you're looking at that full status report. And once it reaches max trials, if it's on continue, it'll generally freeze some of the switching that's allowed and say, hey, if where it was, let's see if I can converge now without allowing any other status changes. That's kind of what those extended trials are, but it's easier troubleshooting with some output rather than no output. So let's go to the Advanced tab. The Advanced tab are things that were added to the EPA. The difference between EPANet 1 and EPANet 2 engine was primarily these. That's one of the biggest changes, in my opinion, from those two versions. I mean, not the only thing that's different, but the key things. And these were things that were added to help model stability. So there's 4 options that are really key up here. The status check frequency, max status check iteration, the relaxation factor, and the damping limit. The 2 that are most helpful when you are seeing a model struggle to converge, we've generally found are the relaxation factor and the damping limit. The relaxation factor, EPANet's default is 0.6. That is generally the best one to use when you're having a model where things are fighting. You'll usually see the default when you have a new model, it's set to 1 because that solves faster. And as long as you're not having things that are fighting, that's often fine. But if you're having a model that's struggling, 0.6, that really helps. Secondarily, the damping limit, and this is something that when you're within 10% of your relative flow error accuracy goal, it's going to start restricting the switching of things. And so that's pretty much, you want to set to 10 times your relative flow accuracy. So if I had 0.001 for my accuracy, my relative flow error, 10 times that would be 0.01. The status check and max status check, if you ever want to talk about those in more in detail, there are definitely a lot of different views out there. One thing that we've found from a lot of different models is that EPANet engine worked best with the default 2 and 10. I would certainly not go any higher than 4 and 20. Anytime I've seen people use higher than that, there's certain times a model can definitely do unexpected things because of how those two work. Those kind of say, hey, when I have a control or something to check, how often do I check it? That's my status check. So I do a trial and I change something, wait 1, then check it again. That's why that 2 and then 10 says, hey, after 10 trials or changes, then stop until preliminary convergence, then check them again. But if your model's converging before that check, when that max status check frequency gets too big, sometimes it unexpectedly causes some weird things. So watch out for that. I definitely would recommend always use 2 and 10, but if you really feel you want to use it, I wouldn't recommend going higher than 4 and 20 at the absolute most, just because it causes some unusual behavior. The last thing that's important here is this newer box called allow disconnected run. The beauty of that is if I've got a node disconnected or some part of my system that gets disconnected, if that's checked on, everything that's still connected, I'll still get results for, and only the areas that were disconnected, I won't. And that's more helpful to at least figure things out when you have some output than no output. So that's usually the only time I'll use that, but that can be very helpful. Now, we keep talking about this. Oh, Tim, you got a question?
Yeah, a couple questions on that last section before I see you're moving into the how to solve the hydraulic status report. There's a question
Okay.
kind of getting into those sections. And again, for those of you maybe you joined later, there is a handouts within GoToWebinar. You can see exactly all the slides Pat's going through and kind of have that for reference later as well. See that in the handout section of GoToWebinar. But in that last section on this slide, exactly, switching check valves. Can you go into a bit more detail? Ben's wondering, what do you mean by switching check valves there?
I'll show an example because I've actually got a model where you see that. I've known a lot of modelers over the years who've always kind of like me. They're like, I try to only include check valves when I absolutely need them because they are a little quirky. Our people who kind of do our, advanced PhD people here have also recommended if you do include check valves, make sure minimum length is 5 feet and make sure their diameter is not excessive. The reason for that is certain checks in the EP9 engine involve how much head loss is going through that pipe. So if it's too big or it's too short, it might have difficulty actually properly working. So that's kind of some of those things that can relate to that. Or,
All right, I guess if you had,
yeah,
I mean, you mentioned pipes near pumps need to have the right direction, but pipes with check valves as well, right, need to have that right direction.
obviously,
Yeah,
because
okay. Just
the drawing directions,
remember.
it's going to say that's the only way it's allowed to flow.
Mhm.
So you're right. That's one of the few other pipes where direction matters.
Mhm.
Most of the time it doesn't, but that's definitely another one.
Yeah. Okay. Perfect. Yeah, we had Andrew asking about kind of the hydraulic status report, how to be able to more efficiently look at that. I think that's a couple slides
Yeah,
ahead here if you
we'll
wanted
have
to
a whole
dive in
bunch of
there.
slides.
But
We'll get into that because that's, to me, really the money part of this presentation.
perfect.
Anything else before we continue, or is that
That's all good. Nope. You answered his question. Perfect. Thanks, Pat.
awesome? Okay, so let's go into what we've been talking about this. What is this full hydraulic status drone report? So you can set this in 2 different places. Again, on the operations tab of the Model Explorer, you'll see the simulation report options are kind of called a little bit differently here. In the Run Manager, it's report options, but over here, it's the simulation report options. You can either double click on it or right click to edit. Or again, this is another place where I'll usually go to the Run Manager or Standard tab and click the 3 dots to open the simulation report. But the hydraulic status right here in the middle, that is essentially the report that will either help you or will not help you. So the no, yes, or status only will tell you something, but it often won't tell you everything. It's only this full hydraulic status report that will tell you exactly what's happening as it's converging. And when you've got a convergence problem, you want to know, tell me everything, because that's really what's going to explain it. The other key factor here at an absolute minimum is make sure you have the generate warning messages checked on. If they're not, it's not going to tell you, hey, this was a problem, and so those are 2 of the key things. If you're troubleshooting a model, want to know what was wrong, the full hydraulic status report and the generate warning messages at an absolute minimum, those are the key. I'm also a big fan of the network summary table because it lists some key parameters in terms of how you were solving the solution. I've always found that at times very useful just to include it, but those are what we would recommend are the best for solving it. Because otherwise, I can't tell you how many times people will contact us and they're like, I've got them all, it's not solving, and it doesn't tell me anything. And we'll look at what they're using, and they're not using the full, and they're not generating the warning messages. And you're absolutely right. If you're not, it won't tell you, and so you're like, what's wrong? I don't know. And so that's the key. You always use the full when you're troubleshooting. Always click on the generate warning messages. I would generally leave those on as default, but certainly if you're troubleshooting, it's essential. So once we have that, how do we decode it? What does it tell you? And so right next to the run manager, there is a little button. Let's see. Downside of having 3 screens here, your mouse gets lost sometimes. Right here, this little button is, it looks like a notepad in InfoWater. That's going to open this status report. So that's how you read it. And if you've got the full one with the generate warning messages, it's going to show you pretty much as it's converging each trial. It's going to show you the details of each trial. So how much relative flow change between the runs occurred. And if you're an InfoWater Pro, it'll also show that as a percentage and as a numerical value. It's basically the percentage is just the numerical value times 100. It's going to show you the status changes. So when there's a simple control or something else that changes based on the solving, like PRV going from active, where it's acting like a PRV, to being closed, because probably the head downstream is higher than the head that the pressure setting is trying to maintain. So it says, hey, you don't need me, I'm going to be closed. The check valve is closed because the head downstream is higher than upstream, so it's going to close that. But it will tell you all those status changes. At the very end, it's going to tell you a summary of the total supply, demand, and stored that was included in that run. And then at the very end, it's going to list, hey, these were the final status changes once I converge. So status of key reservoirs and tanks, as well as elements that change status in that run. And so again, as it's converging, its goal is to get this relative flow change below your relative flow change limit or the accuracy in InfoWater, and then it does some final checks on the simple controls and other things that it changed, and then it says, okay, I'm done. But that's what you will see in this. In the other reports, they tell you much more limited information, but it's this details right here of the trials that's really the most helpful. Okay, so let's look at some of these. Obviously, if you have a problem, your model's not running, your model is stopping, then I need to look at this report, and I want to find one of two things. There's some recent changes that some warning messages are now called caution messages. So search for warning or caution in the run report that shows up. Oftentimes I'll just type in WAR or WARN for warning, because that'll usually find it just as well as typing in the full word warning. But don't forget now to also check caution messages. Any that come up, you definitely want to look at them. It'll list an ID. This element had this warning. So it'll tell you which ID of an element had the problem and what that message was. The description of all those is generally also found in the help. And there's obviously some warnings that are more critical than others. The most common ones that you'll see, and we'll talk about all these in a little more detail in a minute, but maximum trials exceeded is critical because that's telling you, hey, I was struggling to converge, and the answer that I came up with may or may not be ideal. So, but I gave you an answer, but I just want to let you know. Pump can't deliver head. That, as you can see in the picture here, generally means that the system curve is not intersecting the pump curve because it's above the shutoff head and it can't run. Pump can't deliver flow means it's usually operating past that last point on the pump curve. That's important mostly because it's telling you, hey, I'm estimating what the pump curve looks like after this last point. I'm taking the last 2 points and drawing a straight line and, estimating that out, but that may or may not be a great assumption. So it tells you that, if it's close to the end, it's probably fine, but if it's way beyond that last point, it's probably not. You know, Disconnected nodes, I can't satisfy the demand. That's a problem. Got to find out why. Flow control valve can't deliver flow. What all those mean, it's kind of we show on this slide. So, obviously, max trials exceeded means I could not meet the convergence goals within the maximum trials that you told me. If it's still converged because you had to continue on, remember when we were talking about those stop or continue, it may get an answer, but it's kind of a just in case this might be fine or it might not be fine, so it wants to let you know. But it's so much easier to troubleshoot with a possible questionable answer than a no answer. So continue is often more helpful. Again, pump and shut off, you're going to get that can't deliver head, and it'll say something like this: pump ID number closed due to its inability to deliver head at whatever the time was. Pump can't deliver flow, that's past that last point on the multi-point. Pump blank, ID X, but open, but it's exceeding its maximum flow. So just to let you know, hey, I'm guessing how the pump curve shape looks beyond there. Most manufacturers, where they stop the pump curve, it's because anytime it flows beyond, that's going to damage the pump. So that's bad too. So it's a good warning to check. Obviously, disconnected nodes, it's going to tell you the IDs. This node, I could not satisfy its demand at this time. Flow control valve can't deliver flow. That basically means the head upstream is not sufficient to push that flow in this flow setting into the system at that time, but it'll go fully open and say, hey, however much head I've got, I'll push as much flow as I can, but I can't give you what you asked for. Very common. Those are probably the 5 most commonly seen warning and caution messages. The other one I didn't include, but is the negative pressure on demand nodes. I think that's now a caution instead of a warning, but that's also one that's on there. When you're looking at this, and I have several examples that are coming up here, so we'll see what these are in a little more detail, but if I've got elements that are, my model's reaching maximum trials, and I'm seeing elements that are switching on, switching off, switching on, switching off, that's kind of what we're talking about of status changes that are repeating in the run report. If you see that, that's generally what's causing it to not be able to converge. The IDs that are listed that keep changing are definitely the ones that tell you, hey, what's going on there? Why are these 2 things fighting or 3 things fighting? Like I said, if you see PRVs, especially active to open, open to active, active to open, open to close, just cycling through those over and over all the way up to maximum trials, generally that's a pretty clear indicator those things are fighting each other. And so what usually causes that is that the hydraulic grade line, which is the elevation of the element plus its pressure converted from pressure units to HDL units. In SI units, those are the same, meters and meters, but in the US, you're usually in PSI for pressure, so 2.31 feet for PSI, you got to convert those. But if those are within 5 or 10 feet of each other and the valves are close, high chance of those fighting. Not a guarantee, but a high chance they fight. And essentially, usually the solution is just to separate them a little bit more. Sometimes it's even 1 or 2 feet more of separation, and that solves it. Repeated status changes on pump IDs, that's often a clear indicator that there's a unstable control, something that's telling it to turn on and off and on and off and on and off. Like I said, that's usually a control by pressure. That's a very unstable control in the EP solver. Usually the easiest way to round that is to say, turn the pump on by pressure in a simple control and turn the pump off by either a rule-based control, because those have a delay, or turn the pump off by low flow in the discharge pipe of that pump, because you can usually get a correlation there, and that's a little more stable than both on and off by pressure. But just some things to know. So here's some examples, of what does this look like when I'm having something happening. So over here on the right, I've got an excerpt from a full hydraulic status report, and I've got 3 valves that just keep switching between trials, and pretty much just went all the way to max trials, the same thing, just going back and forth. I had 2 that were close to active, so they were now active, and then this other one said, oh, I'm not needed, now I go closed, and then the next trial they just switch, and then they switch back again. It just keeps going. It's like a dog chasing its tail. And so if you looked at those 3 valves and converted their pressure settings to HGLs, so I need to know the valve elevation and their pressure settings so I can come up with those HGLs. I can see, are they too close, and how I might be able to separate them. Most of the time, 0.25 to 0.5 PSI, make one higher in its setting and the other one lower, is pretty justifiable, but that's often enough. And if you look at, hey, which pipes are feeding which PRVs, you can usually tell by design which PRV should probably have the most flow because they're serving the bigger pipe. The other thing to keep in mind there is, a lot of times, if you think about it, it's an HGL that the valve is trying to meet, the hydraulic grade line, not just a pressure, but that's dependent on what the elevation is. In the model, you're often assigning elevations based on the ground elevation, but these valves are buried. And so I'm probably not getting a good value on my valve elevations. I mean, ideally, if I could get centerline elevations for my PRVs, that's probably ideal. But if you can't, there's definitely some uncertainty in my elevations that I've got there. And when they go out and set these, they're usually putting a manual pressure gauge on them. So there's not at best, your settings that you're given are probably plus or minus half a PSI anyway. So adjusting these a little bit is pretty defendable, that it's not too big of a deal, but just be aware of that, if you see this and that's happening, that's often all you'll need to do is just find out which ones are, and then just separate those settings a little bit so that it can make one more likely be in control, and that kind of keeps this chattering. You can have this happen in the real world, and that wears out the PRV. If they actually set these too close and they're fighting in the real world, the PRV just wears out prematurely because it's going open, close, open, close, open, close. So it's the same thing. You kind of see it, just more prone to it in a model. Very common issue for instability. That question about check valves, this is kind of an example. In this case, there was actually a pump that had a pressure control, and there were probably 4 check valves fed by that region that would say, hey, if the pump is off, go ahead and do this, and the pump is on, do this. And so that's kind of, what was happening. But due to that pressure control instability on the pump was also causing repeated check valves to switch periodically. And you can see in this one, it was sometimes waiting a few trials before it said, oh, I need to switch now. But if it's not converging because of this, that's again, it says, hey, this pressure-based control was just unstable. And so I just need to switch how that control is. The on could still be by pressure. That's because that's usually what you want. I want to make sure it comes on when I need it. And then, but the off, I could either switch to a rule base because that's delayed. The simple controls, as you can see, are evaluated as it's converging. Rule-based controls, it waits until the model converges to a solution, then it evaluates them, but it doesn't implement them until the current time plus the rule time shift. So there's a delay. So if you had your off by either low pressure or high pressure, that's usually your off on a pressure-based control, or off by low flow in the discharge pipe, I at least could put a delay and they're not going to keep it from converging. But if they're both simple controls like this, hey, it's too low, I need to turn on. Oh, now it's too high, now I turn off, and then wait, now I turn on again, that's going to be unstable. That's kind of what's happening here. And so sometimes, I don't think it's too often you see instability caused by check valves, but if you see a lot of, and the check valves will show as the CV before it, that's kind of how it tells you, oh, that's a pipe with a check valve. If you see a lot of switching, that's often something to keep an eye on in that full status report, because that's, why is it doing that? Is really what you want to be asking. But again, that's really the root cause in this example was the pump pressure control instability. Another key thing, if you've got a tank that is reaching 100% full, that's the maximum level, then all connected pipes to that tank are going to be temporarily closed. Or if the tank reaches 0% full, same thing, all connected pipes will be temporarily closed. So if you look in your report and you see these words, X element temporarily closed, it's usually a pipe. That's pretty much telling you, hey, I have a pipe, I have a tank that reached max or min level. In this case, min level was 0, so it's pretty easy to see, hey, that went empty. And so it closed the two pipes, and look what happened in the next trial. The pump that was fed from that tank, now the pipe supplying it was closed. It said, hey, I don't have any water supply, I can't run. So it can have other problems, or it might have, in this case, it did not, it had some other way to supply water, so it's still solved, but it may crash right after that tank went empty because it can't get water to supply a region. So that's why, and if that happens, pretty clear that, hey, I need to review what are the control statements on elements that are filling the tank. It's probably not a bad idea to also look at control statements that are draining a tank to see if any of them have an error. But if it's going empty, what's supposed to fill it? Did I forget to put a control in? Sometimes that happens. Or, hey, I put in a control and it just is set up so it's not working. I'll talk about some examples of control issues and common things in a minute, but that's an example of something that you see a lot and can cause a model to crash. So again, what were some of those issues? Well, a common mistake that we sometimes see in a control statement is they'll say that, let's say the max level was 25 feet. They'll say, hey, when the tank reaches 25 feet in a simple control, turn off. But because simple controls always use less than or greater than, and since you can't get higher than the max level, won't ever turn off. Or if there's a min level at 10 feet, and you say, hey, turn on when the tank reaches below 10 feet, can't get below the minimum. So if you have those min or max levels in a control statement, it's not going to work. I think the only place where that can work is in a rule-based control, because those have greater than or equal to as an option. Then it could do it, even though I would generally not recommend using your minimum or maximum levels for control levels because of the pipes closing. But so just watch out for that. That's a very common thing we'll see a lot. Again, watch out for simple controls that are based on pressure values, because an EPA engine does tend to be a little bit more unstable, especially if there's an on and an off in the same simple control. Another common simple control mistake that we'll see a lot is because you don't write a lot of valve controls. So valves with an open status, when you give a valve either from an initial status or a control, an open status, that says, hey, don't act like a valve anymore, you're now an open pipe. Very different than probably what you want to have happen. So watch out for that. To turn a valve on that is off, you need to do that giving it a setting. So setting equals X. Say it's a flow control valve and it's closed, I want to turn it on. Hey, under these conditions, setting equals 500 gallons a minute, so that will turn it on and it'll run at 500 gallons a minute as a flow control valve. But do not use open unless you want the valve to act like an open pipe. So that's a That's what we see a lot. Watch out for that. Same thing with if I want to give a valve that normally runs constantly in initial status, so it has something, give it a none. The none option will tell it use the setting that's in the Model Explorer. If I have a control and I give it a different setting, that might be different than what the Model Explorer says. A lot of times it's the same, but if it's different, the one that's in the control statement will overrule, and that's the one that it's going to use. Other keywords to watch out for. I mean, we talked a little bit about the pipes temporarily closed, because when they reach those max or min levels, that's obviously a problem. If you see disconnected nodes or ill-conditioned error essentially means, hey, I'm trying to find a known head and I can't. But that's often seen in conjunction with those same areas being disconnected. The nice thing that I kind of show here on the bottom, if you get a disconnected node error, there will be in this full hydraulic status report, it'll tell you the link elements that are causing the disconnection, like, hey, there were 70 nodes disconnected due to this pipe, these pumps, this pipe. Some of those you're like, oh yeah, those are normally closed, that's fine. But hey, why did this close? And so you're kind of just working through, but knowing, hey, this tells me, so I can sort of look through those and make sure, oh, should that have been closed or should it not? Definitely helpful. Obviously, as we showed a little bit earlier, if those tanks are going empty and it closes those pipes, it can automatically create disconnections. It's probably the most common thing we see. Another thing is, if in the real world I have two closed valves right next to each other, if you do that in the model, the pipes in between those two closed valves will have no path to a known head, and it'll also give you disconnected nodes. So generally you just open one of those so that it's, because you only really need one of them closed in the model, then it avoids that, but just watch out for that as well. Any questions on that, Tim, that came up before we go to the last section?
No, looks like we're all good. But yeah, if anybody has any questions, please do feel free to submit those. We might go a little bit past the hour. I know Pat warned me, and so for those of you who can stick around, great. If you've got to run, please, and you do want to hear the rest of it, please do just
Yeah, there's only a
email
couple
us.
slides
Yeah.
left here. So, but lastly, if you had a run that didn't complete, then you're usually going to see a yellow light, and usually that hydraulic status report will automatically come up, but you will get partial results. Back in the day, you used to not get those, and it was such a pain because you'd have to go back and, when did it crash, rerun it with a time that was just until it crashed. But it's really nice that now, for about 8-10 years now or so, if not more, it's giving you partial results so that you can say, okay, well, what happened? When this happens, usually the first thing that I recommend checking is to look at what's called the tank group graph. So put all your tanks in a model and then run a group graph on those, and then use the percent volume if you're in Pro, or percent full in InfoWater. Any tanks that are going 0 or 100% full in any time of the simulation are often up, especially if it's right before the crash, then hey, that, as soon as that one closed, then something got disconnected and it died. But if you see any tanks that are reaching those max or min levels, that's often a pretty good indication I probably have either a missing control or a control error there. But if it's crashing, that's usually the first thing I'll do. And here's kind of an example of one of those percent full graphs right there. And so in this case, we had two tanks that were reaching 100% full, which generally you don't want to have happen in a real world because you're going to overflow it. You're losing water, so you don't want that happen. So you probably need to check what's filling these tanks, look at those controls, see why aren't they turning off, because I might have an error, or I might have forgot to put those controls in there. You can see there's kind of, sorry, my apologies for these colors. This yellow and blue are not as easy to see, but if I ran much longer than 24 hours, probably this blue tank down here is going to run out of water because it looks like it's missing a fill control. But if you get somebody else's model that you didn't make and you're looking at it for the first time, just run an EPS and look at the this graph will often give you a sense of, okay, are the controls likely okay, or is there something strange I need to investigate? Those min and max levels, that 0% or 100%, are really good indicators of that. But that's a quick check. Most of the time when I see a model that crashes midway through a run, it's almost 90% of the time a tank that ran out of water or filled up just before the crash. And so you can say, okay, if you've got a system schematic, or a hydraulic profile, so okay, these elements fill this tank. Okay, let's look at those controls. That's very helpful to troubleshoot and look at it. Lastly, a lot of those instability things, if you didn't get any output, are the same problems you can use in troubleshooting. If your model, something may happen and it changes the system operation, so all of a sudden now it's getting to max trials. That's the other kind of issue, and in that case, looking through and saying, okay, what does it tell me? Getting a lot of status switching, in that time that it's not converging. Okay, those IDs help me say that's the problem, and let me look at those controls. What's causing that to switch so much? Usually helps you solve it, and that's pretty much the vast majority of things that people run into in terms of if your model's not running, what would it be? But at least to tell you, if you know these, that's probably 80 to 90% of the time, that's going to help you solve it because you now know where to look. Full hydraulic status report, generate warning messages, look there, use this, download that little PDF that we put on there. If you still need help, feel free to contact us, but knowing these things really, really helps you solve most things you generally will run into. And I think that helps so much. Any other questions, Tim, but before we
Yeah, we can
end here? I
wrap
know we're
up
running out
with
of time.
a couple questions here. Again, we've got a lot of people asking about the recording. Yeah, just shoot one of us really an email, and we'll be able to provide that recording to you. Sometimes we don't post these on the website because we do want people to join live and ask questions and engage and have that kind of dialogue. But you can always email really anyone from Innovyze, and we'll be able to provide that recording if you can tell us the day or the topic you're looking for. Two questions maybe as we wrap up here.
Sure.
Michael asked, I've only used RTC rules. What would be an example of using kind of a simple control?
Most common simple controls you'll see in a water model at least are turn a pump on when the tank level gets low, and then turn off when the tank level gets high. I'd say the vast majority of systems run that way. It's real easy. It's really common to control. So that's probably at least 70% of the controls in most models are generally that form. And in a model, the simple controls is a single statement. So if this, do that. So one condition, one action. I can write multiple ones and they're evaluated top to bottom. If I had something like if this and if this, then do this and this and this, that's what's called a rule-based control. Those are evaluated, like I said, in EPA a little bit differently. Simple controls are on the element, rule-based controls are under the edit rule-based control menu, but those they can be as complicated as you want.
And Alex, I'll do two more questions because I got one more. That's a good kind of wrap up question. If a tank is staying, from Emma though, but if a tank is staying at its max level without overflow, will it continue increasing pressure or just maintain kind of a constant head? So if you hit that max level within the tank, kind of what happens?
So because in the EPA and an engine, when it reaches that level, it's going to close the pipes connected to it, is going to essentially isolate it from the solution. That's why they close it temporarily. What it'll do then is hey, in the next trial, time trial, it'll say, what's the HCl going to be without that tank, and should it open? Like if the HCl is going to drop below let's say it was at the max level, then it'll open those pipes. Or if the HCl outside is then higher and the tank was empty, then it'll say, oh, I'll open and start filling, kind of thing. But that's essentially what it does, but because of that, uh, that's going to isolate the tank from the solution unless you check on that box that says allow overflow. That's a newer feature that will kind of keep that HDL open, and then any extra water, because to keep that HDL constant, I'd have to send that water somewhere. That's basically going to be sent to a virtual overflow that's on there, uh, and that would keep that HDL that's there. One other thing to watch out for is the pipes connected to the tank. Don't make them oversized. Don't make them in diameter or length like 999 or something, massive size. The reason for that is it's those head loss checks. Uh, um, if they can't get head loss, it won't properly close those pipes. So there's times I've seen people make those connecting pipes overly large and the tank went empty, and the EPA net solution to say, hey, I should close this pipe or not, wasn't clicking, and the tank had been empty for like 5 hours. It was still holding that minimum level HGL and providing water. So just watch out for that. It's like once you understand, oh, okay, I see that. So don't oversize those pipes or make them overly long. I mean, I'd say if anything, make it a nominal diameter, based on the filling pipes, and at least a length of 5. That's generally good enough to work, kind of like on the check valve connected pipes, that same kind of thing, of as long as it's not excessively large so that it's almost impossible to get head loss through it unless the flows are astronomical. That's what you want to watch out for. But
Perfect. Yeah, perfect. I think you covered that one. It looks like. And yeah, last question to kind of wrap up here, Roberto. We can get to kind of your question afterwards, but I think this is a good one to kind of wrap on. What would you recommend, kind of Pat, as a starter, a water engineer, to have good habits for modeling or for doing water modeling?
have a design log where you document everything you do. I think when I finally started doing that, that helped more than anything, because it's not hard to remember what you did today, yesterday, but 2 weeks ago, 6 months ago. Why did I do this? What do we do? That's what's really hard. So if you have something where you're documenting it, Excel, OneNote, I think those are fantastic places to do that. Hey, I opened this model. I was working in this scenario. I made these changes. That we'll fix those things. Sorry, I was getting a call here. But be systematic. Learn from every mistake that you make, and you see others make, so that you can. I'm a big fan of, like I said, procedures.
Hmm.
I think you almost have this mental checklist of, okay, I've made these mistakes over there, so now I always check these things.
Right. Yeah.
I really found that very helpful. Um, but honestly, the biggest last thing that really helps is just do model building and model analysis. There's nothing like doing it to really, it's, I think even when we've, over the years trained a lot of younger engineers, it's not until they had them do their first model build that all of a sudden it was like, I get it now, because you're doing it. There's just something about it that you can't replace that. But when you do that and you use it enough, that you start being on there. I'm a big fan. I always ask the question, does this make sense? It's hard to know that when you're young. I don't know if that makes sense or not, but if there's something that you think, this seems a little strange, ask your supervisor, because they should know. Point those out, hey, I saw something, I wasn't sure if this was right or not. Uh, having little helpful sheets, like I made, I don't know if you can see this, but it's like a minimum pipe capacity, based on head loss. Like I use little cheat sheets like this all the time, to know, like, okay, I've got this much flow, roughly what pipe size should be needed, based on different things along transmission lines. So maybe 2.5 feet per second, 5 feet per second is kind of the rule of thumb for maximum, or 10 feet per second for fire flow. At least gives you a sense of what should be there, to make this work, or is what they're likely okay or likely not. Things like that, I think, really help you. But,
Right.
like I said, be consistent, do it. Ask questions always. Don't be afraid to ask questions.
Mhm.
When you're young, you really feel like I should know this, or they'll think I shouldn't have been hired. But that's the worst thing. It's, of course, everyone above you knows you're new. You're not going to know it all. So don't expect that you feel like you have to. Those that ask questions, those that learn from their mistakes, you're you almost can't fail if you do those things. And it's fun stuff, and learn, and like I said, keep a log of what you did, because that really helps you learn from your mistakes, and,
Mhm.
be better in remembering, because there's just so much to remember in modeling that it's hard,
Yeah.
but if you do those
Yeah.
things, I think that really helps you. And
Yeah.
it's,
And we're always here at Innovize, to help with
yeah,
some of those questions you might be struggling with. Pat, the rest of the support team, we're always here to take your phone calls directly, kind of no machine in between. And as far as procedures, we can help you too. Like, where do you start in the very beginning?
yeah,
When we do implementations ourselves, we have a standard kind of set of procedures. Okay,
yeah,
get the GIS information, make sure it's connected, then start checking and looking at pump curves and implementing those, and where are the check valves? Do I actually need this PRV there? Is
yeah,
that going to lead to more instability? Are my tanks far enough apart, or should they just need to be combined into one tank if there are some issues there? And so there's kind of a flow that we know how to go from, starting a model from scratch all the way to kind of fine tuning, that we can kind of help you with. And I think we even have some documentation to share on that as well. So just
yeah,
happy to help with any of that. So yeah, I think that's about it there. Thank you all for joining.
yeah.
Again, if you like the recording, please do let us know. Yeah, thanks, Patch.
All right, bye everyone.
All right, see you, everybody.